Hello. Today we're going to talk about taking or calculating higher order derivatives, which ultimately means we're just going to take the derivative over and over and over again. I want to talk about notation. We're also going to talk about just a little bit of application, but we'll touch on that more in a later topic. So the first thing, and I don't know if you're aware from your physics classes, but if I give you a position function, if you were to take the derivative of position, you'd get velocity. And if you were to take the derivative of velocity, you'd get accelerations. We have kind of a hierarchy here. So again, velocity is the rate of change for position. Acceleration is the rate of change of velocity. And if you think about it, you can make the connection then if I give you a position function, if I ask you questions about acceleration, you would have to take two derivatives. Okay? Take a look at the notation for the derivative below. So I have y prime is the first derivative, y double prime, y triple prime. And then when they start to get to the fourth derivative and greater, they start to put a number in little parentheses next to it. So they're not going to make a million little tick marks. In this case, I have y to the fourth. But it's not to the fourth power, it's the fourth derivative. That's kind of what those little parentheses mean there. Same thing with function notation. And then I want you to take a look at the notation for the dy over dx. So the dy over dx is the first derivative. D squared y over dx squared, d cubed y over dx cubed, so on and so forth. So we're going to try to use proper notation throughout this lesson. And if you have any questions, please email me. So example 1, I want the second derivative of f. So I have to kind of first start by taking the first derivative. So I'm going to start with f prime, and we can just use sum and difference rules here. So I get a 6x squared. Derivative of negative cosine is going to be a positive sine. Derivative of natural log of x is a 1 over x. And the derivative of e to the x is going to still be e to the x. Now, I probably should put on here, we do have this domain restriction. X is going to have to be greater than 0 because, again, we had a natural log in there. It's only defined for x greater than 0. Okay, but now let's take the second derivative. All right, so if I take the derivative using my sum difference rules again, derivative of 6x squared is just going to be a 12x. Derivative of sine of x is going to be cosine of x. Now, the derivative of 1 over x. Now, 1 over x is the same thing as saying x to the negative 1 power. So if I do a little power rule on that, negative 1x to the negative 2, that's a negative 1 over x squared. So the derivative of 1 over x is a negative 1 over x squared, and the derivative of e to the x is still e to the x. And we're going to have the same domain restriction. So this would be the derivative, or the second derivative, of our function. Okay? So ultimately, we're going to do the same steps. We're just going to do them multiple times. Okay? So example 2, I have a scenario. Suppose a ball is dropped from the top of this tower in Dubai. 2,717 feet from the ground. The position equation I give you. So it says compute the velocity of the ball at t equals 5. So I want the instantaneous rate of change at 5. So my velocity function is going to be the derivative of position, right? Which if I take the derivative, if I just do a little power rule here, I'd get a negative 32t minus 10, right? The derivative of 2,717 is just 0. You don't really need to write the 0. So if I want to know the velocity at 5, then I just want the derivative of position at 5. So I have negative 32 times 5 minus 10. And if I do this times minus 10, I get a value of a negative 170. Now I want to put units on that. And if you notice, velocity is going to be a change in distance. So the unit for distance in this problem is going to be feet over the unit of time, in this case, is seconds. So whenever we have an application problem, we always want to try to put units on our answer. So the velocity at 5 seconds is going to be a negative 170 feet per second. So now if I want acceleration, I want to take the derivative of velocity, which is also the second derivative of position. Okay, now I'm just going to take the derivative of our answer above, or the function above. So the derivative of a negative 32t is a negative 32. Derivative of 10 is just 0. So if I want the acceleration when t is 5, I'm just going to get a negative 32. Now this would be feet per second squared. And if you know anything about your physics course, this should make a little sense because this is the acceleration due to gravity, okay? In feet per second squared. Of course, we're not talking about meters per second squared. So that works out for us. All right, let's take a look at another example. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, David Scott demonstrated that a feather and a hammer would fall on the same rate on the moon. And I give you a position function. Okay, what is the ratio of the Earth's gravitational force to the moon's? So the gravitational force is going to be that acceleration due to gravity. So Earth is a negative 9.8 meters per second squared. Okay, the moon we need to figure out. So S of t for the moon is a negative 0.8 t squared plus 2. Velocity, so if I do a little power rule, I'll get a negative 1.6 t plus 0. And then my acceleration would be a negative 3. Hold on. That shouldn't have been squared. Sorry about that, guys. Okay, so let's go back. So my acceleration is going to be just a negative 1.6. And I'm going to put units, meters per second squared. So it says, what is the ratio of Earth to the moon? So the ratio would be a negative 9.8 over a negative 1.6. And if I do that calculation, negative 9.8 divided by 1.6, I get 6.125. Okay, so this is the ratio of the Earth's gravitational pull to the moon's. All right, so let's try something that's a little bit more challenging. I'll show you why here in a second. So I want to find the second derivative of this function, okay? So the second derivative, so let's start by finding the first. So y prime of t, derivative cosecant is going to be a negative cosecant t cotangent t, okay? Now I want the second derivative, which there's a little problem here. So when I do the second derivative, if you notice, my first derivative is a product of two functions. So when I do a second derivative, I need to use product rule. So the derivative of a negative cosecant, okay, the first piece of my product, is going to be a positive cosecant t cotangent t. And then leave the second term the same, cotangent t, plus, now I'm going to keep the first the same, so a negative cosecant t, times the derivative of the second, so the derivative of cotangent is a negative cosecant squared. So if I clean this up, I make this look a little nicer, I'm going to have a cosecant t cotangent squared t plus a cosecant cubed t. Now, if you wanted to factor, you could, but you can also leave your answer just like that. Okay? All right. Now, here's the big one. This is the one I want you guys to pause. I want to make sure you write this down. I want to make sure that you guys follow along in your notes. Okay? So I want the second derivative. Take a look at the notation. That means the second derivative. All right. And we're going to do this with implicit differentiation. So I'm going to start, try to color code this the best I can because this will be a fairly long problem. Okay. So I have my original. All right. So I'm going to take the derivative of this with respect to x. So if I take the derivative of x squared with respect to x, I get a 2x. And if I take the derivative of y squared with respect to x, I get a 2y. But because I'm taking the derivative with respect to x, I have to put a dy dx there, and the derivative of 25 is 0. Okay? Now, what I am going to do is I'm going to get this dy dx all by itself. So let's subtract that 2x over to the other side. Okay? I'm going to divide the 2y over, which gives me a negative 2x over 2y, and I can reduce that to give me a negative x over y. Now, that's the first derivative implicitly, but I want the second. So if I take the second derivative of this, okay, I'm going to show you all the notation here. So I'm going to take the derivative of both sides with respect to x again. Okay, so you can see the d over dx just means I'm going to take the derivative of each side. Now you can kind of understand the notation of why it's d squared y over dx squared, because if you do d, you have two d's on top, right? D squared y, I have two dx's on the bottom, okay? Equals. Now, if I take the derivative of the right side with respect to x, I have to use a quotient rule. So I'm going to do the low times the derivative of the top minus the top times the derivative of the bottom, but the derivative of y is 1 dy dx all over the bottom squared. So I have a y squared on bottom. Now, here is where things get a little messy. I want you guys all to see this dy dx that's in our problem. Okay, we don't want to leave that there. We want this all in terms of x and y. So what I'm going to do is I'm going to write y times a negative 1 is just a negative y. Negative times x is just going to be a plus x times. Now, instead of dy dx, we know dy dx, excuse me here, guys. Sorry about that. We know, my pen is going crazy. All right. dy dx is a negative x over y. So instead of a dy dx, I'm going to put a negative x over y. And then that will all be over still my y squared. Now we can make this look a little better. So I'm going to say negative y plus a negative x squared over y all over y squared. I can even get common denominators. So a negative y squared over y plus a negative x squared over y. And that's all over y squared, which would give me a negative y squared minus x squared over y all over a y squared. And my final answer here would be something like this. Okay, so that would be my second derivative implicit. So there's two steps here. So the first step is you just take the derivative like normal using implicit differentiation. Anytime you take the derivative of y, you're going to get a dy dx, right? So that's all in blue. But then when you take the second derivative, more often than not, you're going to have to take the derivative of this y again. And when you take the derivative of y again, you're going to get a dy dx again. And we're going to substitute the answer from our first derivative into the expression for our second derivative, okay? So again, I took the answer from my first derivative and I substituted it in to to the expression of my second derivative, and that got me the final answer. Hopefully that was helpful. Okay, feel free to rewind, pause, replay if you need to, and I'll see you guys soon.